work as well. But here what I do is I just click anywhere. And I get a potential curve. All along that curve there, the voltage, if this were an electric field, you know, those green arrows were E vectors, the voltage along this thing is like 0.8 or 0.7. You see it up there written out in red. I'm sorry, it's 0.24. This is a scalar potential. This is the number that I'm looking at here. So as I go along here, I'm pretty much getting -1/4 all the way down to right there. That's -0.2 actually, 2.1 or so. And anytime I click, say I click on 1 here, I get a hyperbola. That's the real part of this complex potential, showing you a topography line, as potentials are supposed to. I can just click a whole bunch of them, and I can do the same thing on the axis here, or I can just click anywhere I want, and I'm going to get something. There's a hyperbola going across that way. Okay, so these are, you know, basically a drawing program. This is a very, you know, much slower computer that's running it. It's back in system 9 days. Okay, with the new one, all of this stuff can be drawn all of a millisecond. Okay, as compared to a second or so that it takes to follow the topography lines of this particular function. Okay, so that's what we're dealing with here. So, you know, f of z equal z, figure how dull, how could anything interesting come out of that? Whoa, that's what comes out of it. Okay? But we're not done yet. Go back to the main control here and say, I don't just want the scalar, let's do the vector. Now I could have done them both at once, but I want to take this a step at a time. And so I come back here and I just go up there and I see a little arrow sitting there right there. And I click on that. Whoa! That's what we're getting there is this thing, a vector potential, xy equal a constant. There's an xy equal constant hyperbola, right? This is the streaming potential for this flow, whatever it is, electric field. Well, you never talk about the streaming potential for the flow, but it's the flux. That's where it is, and it's giving it to you just by taking a simple integral of z to get z squared over 2. So that's what I want you to you know, learn about. This is going at physics in a way that lets you actually see things that you might not be aware of. But you see what else we're getting from this. If I were to fill the screen completely with all of these hyperbolas, there's a nice one right there. It's going to be pretty sharp. I go in here, I get one that's, you know, really snaky, okay, and so forth, okay. And now what I'm looking at is curves for which the streaming potential is a constant. As I go along that curve right there, it's a 3.8 curve. If I stay on it, I should be getting 3.8 for the value of the vector potential as I go from any point or anywhere on that particular curve. And the same thing for all of the others. These are more or less symmetric through the 45 degree and minus or 135 degree axis. Okay. All right. Okay. Now, the way this works, if I push some sort of button on that new program, but here it just stopped, takes you back, so you can do other things, and that we have yet to talk about here. But that pretty well takes care of it. Now we're going to go ahead and leave that screen. I want to go ahead just a little bit here and show you what it is that's important about having a potential, and that is when it comes time to actually do line integrals of the field, I don't have to worry about what sort of curve I went on. the line integral of this one will be the same as a line integral from here directly to there, or one that goes and does a loop and comes back to here. All of those line integrals are going to have the same value, and that's the difference of the potential here and here. And that's the difference from complex potential. You get both the streaming and the one that you're used to, the static sort of potential. Now the other thing that we need to do, of course, is go ahead and plot these things. Now there'll be a lot of graphs like this in, this is in chapter 10 of the unit 1, where I go ahead and list the quantities that we're actually talking about in as much detail as it can fit in a little rectangle there. And let's see if there's anything else I need to do here. This computer essentially now is dead, so I'll just work with these two. The next stop here, and that's the important thing for us in the next 2 units, and that is the bonus. The other bonus for this is that you pick a f of z and you get a free coordinate system. Now it is a GCC, but it's a very special kind of GCC. It's called OCC. It's an orthogonal curvilinear coordinate system. We don't need covariance and contrariant vectors for these. And the homeworks that I'm going to give you will be some formidable OCCs. But you go ahead and use the GCC formalism if you want. It's not going to hurt you anything. But in any case, I've used the notation for GCC, the queer coordinate notation, for these two. So there's where you get your Jacobian, right? And you'll find that Jacobian's really simple. And there's a reason for that, and that's called the Riemann-Cauchy of relations, which we're using without really making a fuss about them. We need to make more of a fuss about them shortly here. Okay, now, as I say, this vector field potential theory is easy way into that sort of mathematics. And what I want to show you now, and this is Riemann-Cauchy coming up here, the derivative relations of Riemann and Cauchy. I call it the half and half results. And that's what I mentioned already. And that was that when it came time to use these things, I had the choice. I could just pay attention and take the derivative of the real part and forget about this streaming thing. I should get the same field if I do the curl of this one, and that's what we're trying to show here. So here we are taking a derivative with respect to z star of phi star, and remember that's what we want to use because we're supposed to do that conjugation in order to make this thing not a function of z. And so I write this relationship out in detail here, and we have that relationship. Let me get this one on the same screen down here. I have these relationships that let me express the partial derivatives of x and y in terms of the derivatives with respect to z and z star, or the reverse, which is what I've got right here. So that's what I use. I use the dz z star to write this thing with a plus sign. Okay, and then there's the phi that's got its traditional minus sign. So when we do the 4 terms that come out of this product of binomials, I get this guy and this guy, okay? These 2 guys are equal. They always will be. That's the neat thing about this. It's a symmetry, if you will, that reflects Riemann-Cauchy's relationships. So, we can either look at the gradient and just do that one and not have a half here, or we can look at the curl of the A, the blue lines up there have a curl to them. Look at those with a 1, just call it this, or call it this. Either one, Or I can do half and half, or I can do a third and two-thirds. It doesn't matter. These two are equal. That's something that really you really need to take advantage of that as we do this sort of functional analysis. Okay. Now I note again that this force field using the scalar potential replaces the physicist's usual minus definition. So we keep the minus signs to a minimum by doing that. Okay. So we look at what happens when you take the gradient here. Okay, this is a gradient. Okay, of, and we're only worried about the red guys in this thing, the red lines that have the scalar potential attached to them. And I get this thing, and then I discover that if I take the curl of this, I get the same thing. So that's the key relationship that we get playing this game with the curve and its complex conjugate. And static potential lines and flux potential lines. Pick whichever you're comfortable with. And obviously most physicists are comfortable with the red guys, but the blue wave is coming. Okay, this is an important piece of physics, that flux part of the story here. Okay, is there anything else I need to say? Yeah. These half and half results are called Riemann-Cauchy derivative relations. That's just part of their lore. That is just thrown at you when you get a complex variable. Say, hey, this is what you've got to have in order to have an analytic function. And that statement is very misleading. And we'll try to clarify that a bit. But anyway, that's what makes what happens here. The half and half results of having the x derivative of the real part be equal to the y derivative of the imaginary part, and the y derivative of the real part be equal minus the x derivative of the imaginary part. But here's a physical way to see them. Now, other ways to see these, but that's one of them right there that I point to get started here. Okay, now, there's a little bit of stuff that we need to go through just to avoid the unreasonableness of some statements about analytic functions. The criteria for a field function, to be an analytic function of z, our criteria right now is that function of z must not be a function of z star. That is, this would hold. Okay, that's what we would do if we're sort of doing the stuff we're doing here backwards. We do this either the function itself or complex conjugate. We prefer the latter. But anyway, this is just saying that the differential equation satisfied by this, that is, just go through and take these differential equations directly. Here's the df dz star, here's the df dz, and you go through this algebra, and you have a zero here. That implies the Riemann-Cauchy relationship, x derivative of x equals y derivative of fy, and the logical counterpositive, you might call it, okay, in order to make this zero as well as this. So this goes with this, and this goes with this. Now you could have done this whole thing backwards. Anytime you make some screwy way of doing something in mathematics, very often there's an anti-way. So let's have a criteria for a field function be an analytic function, f of z star of z star. Okay, that's really what we're doing here. But first, f of z star must not be a function of z. This one is not a function of z star. So that's where we say df dz equals 0. But if we do that, you get, I call them, anti-Riemann-Cauchy conditions. Now the minus sign goes on this thing, plus sign goes on that. Okay? So that's just a little bit of a point that I want to make sure that you see the whole story behind this ruse that we're doing here. Now, analytic, when they say analytic, they say, it just means that your function is not showing any singular behavior. That's the usual way of saying the function is analytic, except along this line, or at this particular point. And with our coordinate systems, those points are convergence points where you can't use the coordinate system. Like the center of a polar coordinate system, useless, right? Angles disappeared, radius is 0, okay? Jacobian comes out either infinity or 0, depending on whether it's a Jacobian or a Cudjobian. But let's take this thing. Is that an analytic function of z? Kind of looks like a nice function. It's well behaved. It's not doing anything singular, right? Is that analytic function of z? I don't know. Let's test it using the definitions, okay, of z and z star, or flip those, x and y. Okay, let's test it. Let's put in for x and y these things. And if we do that, if we do put that in to the function 2x plus 4y, we get this. Okay, so far so good. And let's just do it down here as well. So far so good, but we notice after we've done this here and there, that we get 3z minus z star. This is not a function of just z. That's what you mean by analytic function. You mean it's only a function of one of them, or its conjugate would be the function of the other. This one is both. That's not analytic. That's the way you test for analytic. Okay?
Is analytic the same thing as holomorphic?
That's a big word. I don't know, actually. And we have to define holomorphic, and we're not. I haven't done that yet, so I'll say move to that question to start with. Now this one is very famous. The x squared plus y squared. Okay, is that just a function of z? No, that's z star z. So this is not an analytic function of either z or z star. It's a function of both. Okay, that's the key to the idea of analytic. And Riemann-Cauchy relations will not work for any of these. Okay. Now, the one that we just worked with, x squared minus y squared plus 2ixy, that comes, we came about that one honestly. That is an analytic function of z. So that was our field. If you start it, you get this particular diagram. Okay, now, we've got enough time here, I think, to look a little bit at circulation and flux intervals. That is, as we consider what's analytic and what's not. We'll go back to the one we know is an analytic function of z. That's just z starred. And what we're going to do is we're going to integrate that function. But remember, it's f star of z star that we're really working with to make these guys. And we do that because we don't want them to be functions of z, so they have 0 curl and 0 divergence everywhere, except at a singularity. So here, when I do this integral and have made the integral using the idea that it is analytic, so I can just subtract these two guys from each other. The delta phi will be the combination of del phi and del A. If I do that, I need to do a couple of things here in order to explain what each of those real and imaginary parts that are going to be coming out of this integral are. So we start with just the integral of f of z dz using f of z. But I know we're working with f star of z star, so I've got to do f star of z star star, and then do the integral with respect to z. Okay. That in order to get the idea that we would have here, that you don't have to do the integral, you just simply have to subtract the endpoints from each other. And that's all what's going to come out of this. But what is it that we're actually measuring with the integral? That's the thing we try to answer here. So, I have here, after having done this with the thing here, got the things that I need to multiply together, I get a real part that comes out to be a line integral, which we're fairly familiar with. That's just a force dot distance here moving. That's work integral there with the wrong sign, but we're trying to be mathematicians now instead of physicists. And then this thing right here comes out, F cross dr, and it's kind of messy looking, but if I flip the dot and the r, then I get a thing here that looks like a flux integral. So this is a line integral. This is it's tracking the amount of force that you're feeling along the line, and this one is tracking the amount is crossing the line. Try to draw that, a picture of that. It's not easy. I should have had this thing up there all this time, but that's the picture that I'm trying to sell you in this particular deal here. So, if you just want to work with scalar potential, fine, go ahead. But this is another way to do the same problem that's giving you a flux integral. This one is just how much do we have along a curve summed up. And this is how much we encounter crossing the curve summed up. And that's kind of neat. Okay, that's a kind of a neat thing to see, because that's, after all, what the integral represents. First the real part, then the imaginary part. So yeah, that's a part of the story that we want to tell about these integrals. Okay, we've got a few more minutes here. I think we can go up to pretty close the halfway point for this particular lecture, and that's this one right here. And that's where we actually look at the topography lines. Here the scalar potential is stereo plotted, and that's what this, and the computer, the one that TC is trying to bring kicking and screaming into the HTML world. The basic idea is there's a physical interpretation that you know very well for the scalar potential lines, and they're just representing altitude, constant altitude on a graph that shows the real part of the potential, the phi, we call the scalar potential in physics. And then the only thing that makes this a little bit weird is that we've got a minus sign that's missing from our gradient of phi. The physicist's gradient of phi would be the actual force, and we're talking about the mathematician's force that is holding the thing back against the slope of that. So if we can go ahead and I'm going to go over and look at this graph right here with its curves that it has memorized, and we're going to be doing the same thing, memorizing whatever curves you make, and then you erase them when you're tired of them. But I don't know here. What I want to plot is the 3D picture of that real part of the potential, the phi function. And there's a pretty good picture of it. Now, the thing that we have available to us, and will have much better available to us, control position that, but you can see what it is. It's a beautiful saddle point in the middle, and then a saddle that goes infinitely in all of the directions. And if you turn that thing up, sort of, I'm going to try to move it up and get these things sort of lined up in a funny kind of way, so you can see that they really are straight lines. I forget how to do this now. I'm going to try to bring it up sort of like that. Let's see if that works out pretty well. I think you can see it now, that all of the curves that are curvy there, I'm looking edge on, and they're all straight lines. okay? Now what about those other lines? Think of it as these red things are tracking your voltage, okay? And then the gradient in voltage, along the gradient of the voltage is flowing, well, what better to say than water, okay? There's some blue water flowing along these. Now the minus sign makes it so they're flowing up. That's the mathematician's way of defining things, but fine. That gives you a pretty good picture of what it is we're dealing with. And if I drag it this way, then you can see the hyperbolas. If I were to bring the thing, crosswise, to see if I get it directly edge on, z-axis on, you see the hyperbolas for both of the equal potential lines, scalar and vector. Okay, now what we hope to have, and this is a little bit gilding the lily, but we should be able to plot this either in a cross-eye 3D, which would work in a large auditorium like this one. This is a large auditorium compared to what you have when you have a computer screen that's right in front of your face. If you have a computer screen, wall-eyeing is very easy to do. You can just relax your eyes so that this eye looks at the right image and this eye looks at the left image, left eye and left image. For looking in this room here, the way you do that, and people in biophysics learn to do this with big molecules, is you plot the, I'm going to get rid of the XY grid on this plot and plot 3D again here in stereo. I'm going to use wall eye just for the thing. So if you were to look in your textbook, you would see a diagram like this. And then you wall eye it and you can see it in 3D. For complicated potential, it's really a big help. So I'm going to zoom in that's a little bit there. But you can move those too. And we're going to have ways to do that with the thing. Now, wall eyeing is not possible for images that big. Wall eyeing works if the images are about the width of 69 to 72 millimeters between the average person's eyes to do stereo viewing. But cross-eyeing, let's go back here, cross-eyeing works, and let's see what that looks like. The cross-eyeing allows you to, basically what you do is when you look at the screen, you will see, if you hold your finger up, you'll see two fingers. If you're looking at the image up there, you're going to see two fingers, and the idea is to put those two fingers right on the origin of the two plots, one finger on one plot and the other, and then look at your finger, and it will bring those two images together if you can control the focus. The idea is not to immediately focus on your finger. Eventually you do focus on the screen, but at first you just focus on your finger. And the two images will swing together, and if you're lucky, they'll lock. The 3D computation that's going on in your brain will lock in on a single 3D image. So if you ever go to a biophysics lecture where they're showing big molecules that are, in 3D, that's the way you do it. Okay? All right, well, what's going to happen in the next lecture is some more complicated functions. We've just done f of z equals z. Okay? The next one to look at is f of z equal 1 over z. And that's the source. That's the thing that gives you monopoles, current, vortices, all that kind of stuff. And if you make it complex, it makes galaxies. So we've got some things to do here. Just with z and 1 over z. Then we take derivatives of those, and we get z squared, 1 over z squared, okay? You see how we get all the crazy coordinate systems that make up a lot of the mathematical physics of orthogonal, so-called OCC coordinates. Okay, We'll see you.
Meromorphic functions.
The which?
Meromorphic functions.
Is it meromorphic?
Meromorphic functions are holomorphic functions except at the poles.
Except that.
Except at the poles.
At the poles. Okay.